Hello everyone. Today we're gonna to introduce a special course in algebra, which is linear algebra. Let's write out the topic. So, as you can see, it holds the definition of algebra and its linearity. So let's introduce. What does algebra study? You may ask. So it's about definitions, theorems, proofs, and the most important, structure. So what we really care about is about the linear part in algebra, not the whole algebra. So you may ask, what is linear? So what is a linear? Like 2 plus 3 and 2 times 3, which you can clearly see that this plus sign is something that adds 3 to 2, and this multiple is what scale 3 2 times. So from these two simple examples, you can see the essence of the linear algebra by looking at the scaling and vector multiplication. So let's start. These are common binary operations for numbers and vectors. Now, to formally introduce vector space, we first want to know what is commutative, and associative. Like our simple example before, 1 plus 2 equals 2 plus 1, because the multiplication and wait a second, 2, yeah, because the addition and multiplication are both commutative. Which can be written in an abstract way, which is x plus y equals y plus x. We can switch the order of adding, which means that the order does not matter for two elements to add together. So this is commutative. And the notation for associative is, which includes three objects, x plus y plus d equals x plus y first and plus d, which is also easy to understand as you can have more brackets to add on. So let's think about some solid examples that is there any binary operation that is not commutative? Yeah, subtraction. And any binary operation which is not associative, which is also subtraction. and division if you want to try it at home. So this leads us to the axioms of a field. So what is field? Field is a set F where we have two binary operations. And there are 8 axioms of a field, which where addition and multiplication holds for all the vectors in this field. So that's right. 1, associative. 2, the two operations are commutative. And 3, so if we can find the dual vector where which means that we are going to think that if this adds to x, this will not change the value of x. If this multiplication identity multiply x, this will not also change the value of x, because 1 multiply everything equals everything. Yeah. And 4 is there's an additive inverse x prime such that x plus x prime equals 0. So you may ask why we define x prime things like this, because there's not always a scalar zero in a field. There's not always this case. But what we can have is that for every x, we have its additive inverse to make them add together to be the additive identity. And which naturally leads to the definition of the multiplicative inverse. So this is multiplicative inverse. And for number 6, that's distributive and yeah, which means A times B plus C equals A times B plus A times C. Now, let's try to make something more familiar with this, which is the imaginary root. As we defined, the imaginary root is the square root of -1, which means all complex numbers have the form of where A, B are all real numbers. And you can draw any number Z as a vector in a space where we can see this is imaginary Z, this is real part of D, and this is D, denoted with an combination of two numbers A, comma B in our plan. So after the field introduction, let's see what is a vector space. Vector space is very similar to the definition of field where we have and there are 8 laws. Which you may think that is quite familiar, because we have seen them all in the definition of field. The A6 is distribute scalar multiplication, like C plus D times X equals C times X plus D times X, where A7 is associative, where we have CD times X equals C times D times X. And the last is the multiplicative identity. Yeah, here we go. So let's talk about something more familiar for all of us, which is Rn. We can see that Rn equals the set where we have components, right? The n components, which denote the n dimensions of numbers, where in a vector you put n numbers at n different places. So you may ask, what is the addition operation? It is x1, x2 plus y1, y2 equals x1 plus y1, x2 plus y2. And the scalar multiplication is C x1, x2 equals C x1, C x2. The C times each component. To scalar or to stretch or squeeze them C times as the original vector. Yeah. So I will not cover formal proofs, but I will just, how can I say, provide some idea for intuition to understand things more easily. So how about more down-to-earth examples? Well, let's see how to do this. 1, 2, 3 plus 2 times 1, 1, 1 plus 3, 2, 1. You may be familiar with this type of question, but let's revisit it. First, we should know that we should calculate the things in the bracket first, which is 1 minus 3, 1 minus 2, 1 minus 1. Yeah, why we do that is that by definition, plus here is now minus here. So you minus subtract the second component from the first component of each component of the vectors. Let me repeat, it is a one-to-one relationship. Now you scale them by 2, which is, and now we use the addition again to get the final result. It's worth noticing that we began with things like ABC and end with ABC, which is a little bit not surprising, right? But we will show that in the following courses. By the way, talking about ABC, what do you think about now? If we choose xy, x3, x1, x2, x3 as the 3 components, so there we have the intuition to break down, which is very important, that you can write a vector like this. Okay, this is a very important notation for vectors. So, as we mentioned before, and many people will have misunderstanding here, that this is a vector and its components are all numbers, which means we can write them as the addition of 3 vectors. Here we go. And we now revisit the scaling which means that you time a vector, you stretch a vector by a scalar. So what is a scalar in our expression now? Oh, it's x1. So you stretch this by x1 times, like this is 1, and you stretch it by x1 times. And this is exactly what you got. And then compare the form that we get. Clearly, this is about that, oh, we have three vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. And for each vector, we stretch them by x1 times, x2 times, x3 times, and then add them together to get our x. Note that the choosing or the choice about x1, x2, x3 is really arbitrary. So, which means we can express any number in R3 with this method. So, as we mentioned that we can write any vectors, let's solve a question together. Okay, so our result is this, and x1 here is, suppose x times 1, 2 plus y times 1, 1. Or if you like, you can also write like this. They're the same form. So this means that we scale this 1, 2 x times, scale 1, 1 y times, and add them together, which gets x plus y, 2x plus y. Okay. Now, for equality, we have this system of equation which x plus 1 equals negative 1, 2x plus y equals 1. So, by what we learned to solve them, this is the result if you're interested. And if we have the vector space for numbers, and we can have vector space for functions, which we specify in this course, real value functions, which takes a real number to another real number. So you may have seen this in high school where you may write like y1 equals x, y2 equals 1. So what is y equals y1 plus y2? Oh, this is clearly x plus 1. So the addition of this is f plus gx equals fx plus gx. And the scalar multiplication is now we got this. Yeah. And next part, which is you may formally hear about of matrices, is matrix. So what matrix mm, is a set of numbers or a bunch of numbers where you can write them. So don't be shocked by the expression of the matrices. We're gonna to cracking them one by one. Like it is where you put numbers as components of vectors. And let's write a 2 by 2 matrix, which is, yeah. So as we see the example, we have to define the multiplication. It seems intuitively that since matrices are putting numbers in them, so their addition must satisfy the rules of the addition of numbers. Now, this is matrix. And how about some down-to-earth example again? Which is do you understand it? Because this is scalar multiplication and this is addition. Yeah. All right. We have to show something in the axioms, right? What if someone asks that is this unique? Now we can show this. Suppose and so this means that we add this to the vector to this vector, and this does not change the value, right? And this is
commutative of adding. And here we go to use the property of the delta vector again. So now we get that delta prime equals 0. So the delta vector is unique. And now let's oh, this seems obvious because let's use the x. If we can prove something like this, we can know that this is zero by the definition of the delta factor. So let's add z first. This is now at the additive inverse to it, we got and notice that the two parts is by the definition of the additive inverse. There we go. And if you want to know that what exactly additive inverse is, we know that this is always negative x. So how to prove that? We just prove that whether their addition is zero. So this is what we proved last time. So this also leads us to the delta vector. And now we give a definition of subspace, which is W is also a vector space, which lives inside V, and you can think something like this. So it must follow V rules, right? So the first we want to have is we want to show that the delta vector lives in W as well, and the second is closed under addition and scalar multiplication. This is very not that intuitive because we're trying to see that if we have x, y, so c times x plus y is also lives in W, which means as you stretch a vector and add to another vector, oh, the result also lives in a vector space.
Okay, let's start. So this means that for there are examples that x equals y equals 0 for only the zero vector. So as you stretch, the zero vector is always the zero vector. A line, as you add them together, they will always leave the line that the y component is always zero, or the whole plane. Yeah. So why does a vector space or its subspace have so much forms? We are so confused about this because they're actually parts of vector spaces. The parts means that less than or equal. So as the vector space, its subspace contains all the combinations. If the dimension is less than it, all the combination gives a line. If the dimension equals itself, all the combination gives the whole plane again. So that's is all the content for the week 1 of linear algebra. Thank you for listening.